Hi everyone, this is Kiranmay from H&S department. Today we are going to have an introduction for semiconductor physics and different types of semiconductors. So coming to the semiconductors, a semiconductor is not as a solid material which is having fully filled valency band, which is separated from a empty conduction band by a forbidden gap at absolute zero. As we know earlier itself, materials are of three types: conductors, semiconductors, and insulators. Coming to the conductors and insulators, they are having unique features like conductors always conduct electricity, insulators oppose electricity or the passage of current through them because of a very high forbidden gap. But semiconductors has a feeble nature that they can behave both as a conductor and an insulator, which makes them more prominent than a conductor and insulator to work in the today's day-to-day life. And coming to the structure of a semiconductor material, semiconductor is having a fully filled valency band with a empty conduction band with a small forbidden gap between them. This gap is usually very narrow in semiconductors, so that at finite temperatures, if you give a small temperature also, electrons can be excited from the valency band to conduction band easily, and they become free over there. And further increase of temperature, more and more electrons will be excited from valency band to conduction band, and holes will be created in the valency band. Hence, in these materials, it is possible to control the carrier concentration, which means that as you increase the temperature, electrons will be excited from valency band to conduction band. If you go on decreasing the temperature, obviously electrons will come back to its original place. Hence, we can change its carrier concentration by increasing or decreasing the temperatures. On the other hand, in metals and insulators, this type of control is not possible by any means, either by temperature or by any doping elements. We cannot control the flow of electrons in either in conductors or in insulators. But in semiconductors, we can easily control the carrier concentration by increasing the temperature or by adding a impurity element to the material. So coming to this adding of impurity and increasing the temperature, these are the mechanisms by which we can control the flow of carriers in the semiconductors. So these are broadly two types. One is thermal effects, which means that by changing the temperature, another by doping, which means that by adding the impurities to the pure semiconductor material. So thermal effects, where a finite temperature, there is certain number of electrons that are excited from valency band to empty conduction band, and as the temperature is increased furthermore, the number of exciting electrons also increases. So the properties are determined by the inherent nature of the element themselves. Such semiconductors are classified as pure or intrinsic semiconductors. Whereas when you go for the doping, a suitable highly doped semiconductors at low temperatures will bring about a change in charge carrier concentration. The properties of such semiconductors are therefore controlled by nature and amount of impurities added to it. So such semiconductors are classified as extrinsic semiconductors. Coming to the first one, that is intrinsic semiconductor. As I told you earlier itself, in this we are just going with the inherent nature of the semiconductor material, not by adding any sort of impurity to the material. So an intrinsic semiconductor is also called as a pure semiconductor, or an undoped semiconductor, or an I-type semiconductor. These are the different names for the intrinsic semiconductor, depending upon its nature. So a pure semiconductor without any significant dopant species present in it is nothing but an intrinsic semiconductor. The number of charge carriers therefore determine the properties of the material itself instead of the amount of impurities in it, as its properties can be inherent to the material. So carriers will be number of carriers produced in the material will be determined by its properties itself, not by the doping element. So the best example for the intrinsic or a pure semiconductor are germanium and silicon. Coming to the structural nature of intrinsic semiconductor, generally semiconductors will have 4 valency electrons. So when it forms a structure, all 4 valency electrons try to bond with 4 more electrons of 4 four more electrons of other semiconductor atoms. Like on the screen, you can see the silicon structure where every silicon is getting attached with four more silicon atoms with the four valency electrons, thereby forming covalent bond between them. Okay, and the electrons which are left free, which are not bonded with the other silicon atoms which are on the surface of the material, they are called valency electrons. Coming to the band structure of intrinsic semiconductor. So if you won't give any energy or a temperature to the intrinsic semiconductor, there is no excitation of electrons from valency band to conduction band. Hence, the structure will be like a completely filled valency band with an empty conduction band, as similar as an insulator. So at 0 degree Kelvin, an intrinsic semiconductor behaves like an insulator. That was the first point, where it states that the band structure of intrinsic semiconductor at 0 degree Kelvin is not unlike to that of the insulators. So there is a vacant conduction band separated by energy gap from the fully filled valency band. So at absolute temperature, there is no electric conduction is not possible, as there is no excitation of electrons from valency band to conduction. But if you increase the temperature of the material, what happens? Electrons are thermally excited from the valency band to conduction band, where they become free or conduction electrons. Hence, electron hole pairs are created. Electron hole pairs means as the excitation of electrons from the valency band to conduction band creates a vacancy in the valency band. That vacant space is called as a hole. So obviously, when an electron is excited to conduction band, one vacant place position will be created in valency band, which is called as hole. So always electron and hole will be created in pairs in an intrinsic semiconductor. So the number of electrons in the conduction band is always equal to number of holes in the valency band for an intrinsic semiconductor. So let us see the energy band diagram for an intrinsic semiconductor at 0 degree Kelvin and T degree Kelvin. So on the screen, you can observe that at 0 degree Kelvin, all the electrons are present in valency band and there is an empty conduction band, and it is separated by an energy gap Eg. Let EC be the minimum of the conduction band and EV be the maximum of the valency band. Now, as you increase the temperature from 0 degree Kelvin to T degree Kelvin, what happens? Slowly electrons absorb that energy, thermal energy, and they will excite from valency band to conduction band, leaving a hole in the valency band. So obviously at T degree Kelvin, the number of electrons which are present in the conduction band is always equal to number of holes which are present in the valency band. This is the basic condition for an intrinsic semiconductor. That is, the number of electrons in the conduction band is always equal to number of holes in the valency band. This is in case of an intrinsic semiconductor or an I-type semiconductor. Now let us go for the extrinsic semiconductor. So extrinsic semiconductor is a material in which charge carrier originates from the impurity atoms, not by the inherent of the material. They are added to the material. Since we are adding an impurity to the material, these semiconductors are otherwise called as extrinsic semiconductors or impurity semiconductors. Extrinsic semiconductors are impurity semiconductors, and their electrical properties of the pure semiconductors are drastically modified by the addition of certain impurities, because when we come for the extrinsic semiconductor, here the electrical properties depends both on the semiconductor material and also the impurity what we had added to that material. So the process of adding such impurities to the pure semiconductor material is called as doping. This can be done with two different impurities. One is pentavalent, another one is trivalent. Pentavalent impurity, example arsenic, antimony, bismuth, and trivalent impurities, the examples of boron, aluminum, and gallium. Coming to the N-type and coming to the N-type semiconductor, this N-type semiconductor can be prepared by doping a pure semiconductor material with pentavalent element. which is having 5 valency electrons. In the name itself, it is specifying that pentavalent. Pentavalent means 5 valent electrons will be present in the material. So when you add such type of impurity to a intrinsic semiconductor in small traces, then such type of extrinsic semiconductor is called as N-type extrinsic semiconductor. Now, what happens to these 5 valency electrons of the pentavalent element? Out of the 5 valency electrons of the pentavalent element, 4 will get bonded with the 4 semiconductor atoms of the material, and 1 electron is left free, which is weakly bound to the atom. So this electron, when you give lesser thermal energy also, this 5th electron is ready to leave its parent atom and making its parent atom to be positively ionized. In the energy level diagram, the energy, when you see the energy level diagram, this 5th electron belonging to the donor atom, its energy level is very near to the conduction band, just below the conduction band. The electron in the donor level gets excited to conduction band at room temperature itself. Hence, majority of charge carriers in N-type semiconductor are electrons and holes are the minority charge carriers. So coming to the structure of a N-type extrinsic semiconductor, on the screen you can see that germanium material doped with an arsenic, where 4 arsenic 4 electrons of the arsenic got bonded with 4 germanium atoms, and 1 electron is left free, which we will call it as free electron. Okay, and this electron is ready to get out of the parent atom even at lower temperatures itself. That's why more number of electrons are present in N-type extrinsic semiconductor. Coming to the energy level diagram, see here on the screen you can observe that fully filled valency band with an empty conduction band, and a donor level will be very nearer to the conduction band, which is having donor atoms ready to donate its 5th electron. Now, when you increase the temperature from 0 degree Kelvin to T degree Kelvin, these electrons which are present in the donor atoms, even for the lower increase of temperature, that 5th electron will get excited to conduction band. So obviously in this state, we can say that at lower temperatures, the number of electrons in the conduction band is equal to number of ionized atoms in the donor level. These are ionized atoms. They had given the electron, means they are positively ionized atoms. So since they had donated the electrons, we can call them as positive ions. So the number of electrons in conduction band is equal to number of positively ionized atoms in the donor level. So for a N-type extrinsic semiconductor, the basic condition is the number of at lower temperature, the number of electrons in the conduction band is equal to number of positively ionized atoms in the donor level. Now coming to the next type of semiconductor, that is P-type semiconductor. Here the trivalent elements are doped to the pure semiconductor material. Trivalent, in the name itself, it is mentioning that they are having 3 valency electrons. So this type of 3 valency electrons, this type of semiconductor material are called as P-type extrinsic semiconductors. So out of the 3 valency electrons of the trivalent element, all these 3 will get engaged in the covalent bond with the 3 neighboring semiconductor atoms, and they need one more electron to get bonded with the 4th semiconductor atom. So this trivalent element is ready to accept an electron to form a bond with the semiconductor atom. Hence, these elements are otherwise called as acceptor atoms, and the energy level belonging to these impurity atoms is called as acceptor level. And this level lies just above the valency band. Even at relatively low temperatures itself, this acceptor level accepts electrons from the valency band by making those atoms as negatively ionized. Hence, due to excitation of electrons from valency band to acceptor level, holes will be created in the valency band. Hence, in P-type semiconductor, holes are the majority carriers and electrons are the minority carriers. Now, let us see the structural figure for a P-type semiconductor, where germanium is bonded with boron. Hence, Boron is having 3 valency electrons. It was got bonded with 3 germanium atoms, and it is ready to accept one more electron to form a covalent bond with one more germanium atom. So to get this atom, it is ready to accept the electron at low temperatures itself. It will accept an electron from the valency band and make a covalent bond with the germanium atoms, making that trivalent element to be negatively ionized. Coming to the energy band structure, here in this, the fully filled valency band and an empty conduction band, when it is doped with accepting atoms, acceptor level is just above the valency band. Now, if you increase the temperature from 0 degree Kelvin to T degree Kelvin, what happens? The electrons from the valency band slowly excites from valency band to acceptor level, making those acceptor atoms to be negatively ionized. So the number of electrons excited to acceptor level makes that much number of negatively ionized atoms in the acceptor level and that much number of holes in the valency band. So for a p-type semiconductor, the condition is the number of negatively ionized atoms in the acceptor level is equal to the number of holes produced in the valency band at lower temperatures. So what are the 3 different conditions we got for the 3 semiconductors? That is, for I-type, at low temperatures, number of electrons in conduction band is equal to number of holes in valency band. For N-type, number of electrons in conduction band is equal to number of positively ionized atoms in donor level. For P-type, number of negatively ionized atoms in acceptor level is equal to number of holes in the valency band. These are the 3 different conditions which are further used for the derivation of carrier concentration of different semiconductor materials. Coming back to the types of semiconductors, depending upon the energy gap present in the materials, there are 2 different types of direct indirect band gap semiconductors. So depending upon the gap between the conduction level to valency level, these are like direct and indirect band gap semiconductors. So coming to the direct band gap semiconductors, in this the maximum of valency band occurs at the same K value of minimum of conduction band. See here, the minimum of conduction band is having the same K value as of the maximum of valency band. So this type of semiconductor materials are called as direct band gap semiconductors. Whereas when you go for the indirect band gap semiconductors, the maximum of valency band does not have the same K value as of the minimum of conduction band. So here the direct transitions from valency to conduction band is not possible. Whereas in direct semiconductors, the transition from valency band to conduction band is very easier. So direct transitions are more easier than the indirect transitions. Hence, the transition of charge carriers across the band gap is more in band gap semiconductors than in indirect band gap semiconductors. So this is all about the types of semiconductors, what we had discussed today in this session, like I-type semiconductor or a pure semiconductor or an intrinsic semiconductor. Next one, 2 different types of extrinsic semiconductors with p-type and n-type. And the last differentiation between semiconductors depending upon the band gap is direct and indirect band gap semiconductors. Thank you.